So we eventually figured out that it's the switching time of the power that is most critical, and that is achieved in lots of different ways. And this machine is done mechanically, or it can also be done with electronic switching.
その電気の切り替え、スイッチする時のタイミングが重要なので、機械式にもできるし、電気式にもできるということは分かった。
Oh, here's the results to that if you like to keep it. So, as you in the original one that we showed you the first time in this room, the little tiny one, it was only capable of handling about 30 watts. We had more trouble with the switching arrangement than that. That it was very, very difficult to scale it up.
30ワットからスケールアップさせて、なかなか難しい問題があります。
Since that time, Eric has developed a new control module and a new switching module, and we've had a larger set of capacitors to store the energy.
This is the control.
Yeah.
And this is the switching.
Switching, right.
And this is the capacitor to store energy.
Yes.
エネルギーを貯蓄するキャパシターと新しいスイッチと新しいコントロールパネルをそれあれ以外に開発している。
So these segments are all new. The one that we showed you before was a little tiny computer-driven model.
これはもうですから新しい前回お見せしたものとは違います。
And this one is much more flexible, and it allows us to control the wave function geometry, which in turn gives you the resulting change in efficiencies that we're going to show you.
この機械は非常に高い能力がありまして、いわゆる電波の波形まで変える。それが結局そのより優れた効率につながっている。
Now, we have it set right now to imitate approximately the results we gave you the first time.
これ今ですね、どこにセットしているかというと、前回お見せしたものと同じようなところにセットしてあります。
So, in this resistor, which is the load now, we are dissipating about a little less than 32 watts.
これ前回32ワット
So from the
同
line,
じところにセットして
from the line, we're pulling almost 11 watts, 10.97, 10.98 watts. Now, what we're going to show you is, and the reason I have the scope on here is so that you can watch the waveforms change in accordance with the changing efficiencies that we're going to show you.
効率が変わるたびにこの波形が変わってくるんですよ。
Eric, you want to take over and the first thing we want to do is probably bring it down.
まず下げます。
Now, what he's doing now, if you watch the waveforms changing, you can see that the geometry of the waves changes in accordance with the results. We are now dialing down so that the input power is only...
It's all the way down for the current setting I have.
Okay, so right now we're only pulling 1.5 watts from the wall, and we're still giving you 33 point...
今1.5ワットして壁から1.5ワット取ってでもこっちが30ワット出してます。
But we'll leave this setting fixed for the moment. Eric, crank it up. Now, we're going to show you that we're not limited anymore to 30 watts.
だから30ワットじゃなくて今度はね100ワットも出せると。
So now we got 100 watts in the load, and we're pulling 5 watts. That's 2,000%.
電源が5ワットでこっちが100ワットで。
The resistor's going to get pretty hot.
Yeah, we can't leave it on too long. It'll smoke. But you can put your hand on there. It's bloody hot.
これは実験機ですから熱くなっちゃうんでそう長くは置いとけませんけども。
それは深そう。
そう負荷ですよ。
なるほどね。
負荷のキャパシター。
Now, we have one other little thing to show you, and it's pretty startling. If you continue to change the waveforms appropriately on this, due to the way that these capacitors are made to operate with these switches, we can actually send back more current than we take from the line. And that results in these wattages going negative.
今度はですね、
Oh my God.
逆にね、あっちに電波を送り返すことができる。
So that means we are still dissipating 102 watts in the resistor, but we're sending back 30 watts to the power company.
100ワット使いながらなおかつ30ワットもここに壁の方に電源に送り戻してる。
Now, the implications of that, if we can marry this with even your standard wind generators right now, the power that's going back will help it to turn like a motor, and you'll operate with less wind.
That's one of the applications. For starters.
発電してるからってさらに羽をこう回す力になる。
Now, question in relation
風でも動くようになる。
in relation to the mix you're getting from the grid.
Yeah, it's starting to smoke. Turn it down a little.
In relation to the mix you're getting from the grid, you're getting reactive energy and
No, see, this is, well, yes and no. You have to understand that in a normal situation, reactive power is defined as a form of restorative power in which the average value is zero.
correct. Yeah.
The problem with that is that the current and the voltage are usually out of phase by 90 degrees, which means that you can't use it.
Right.
What this device allows you to do is to create watts that are doing the same thing of going back and forth. So the wattage becomes reactive.
Got you.
Wow.
See, here's the thing. In Japan, average wind is like 2 meters. So if we could bring it down to the we can rotate up by 1 meter wind. That makes a huge impact.
Yes.
Well,
That's
as soon as we have the funds to do so, I would like to get a standard alternator that you guys use, or whatever kind of generator you use, and try to marry this system with that, put the instruments on it to see how fast it's turning, and then see what the effect is.
Now, what effect? Let's say on a global scale, on a large scale. Say there's 100 million units like this in America. What effect would that have on the grid?
Okay, that's a very interesting question, and I know the answer to it because I researched it thoroughly. Tesla himself said 100 years ago that if we used reactive power instead of the normal kilowatts, and he was referring to reactive kilowatts, not the normal reactive, that our present transmission grids could bear 1,000 times the load that it can sustain right now for exactly the same fuel consumption. And that's not an exaggeration.
But the question was, the effect of this on a global scale with 100 million units in America, everybody having one of these, what would happen to the grid?
もし家庭にこういうのがアメリカ中に入ったとしたら
The
answer was
And the answer is that Tesla predicted 100 years ago that if you did this judiciously, and everybody was returning the majority of the power they're using back and forth, that the same grids that we use now, the same generating facilities that we use now, could sustain 1,000 times the power that we can deliver now for the same fuel consumption.
100年前ですよ。もしこれを各家庭に持たせたとしたら、
We've been ripped off.
その配電装置と発電装置。
How do you meter it? That's where Tesla got killed.
Well, no, you meter it the same way. The problem is it changes the economics of the thing drastically. So, that's why J.P. Morgan said, pardon me while I pull the plug.
Yeah, right.
But if we get to the point in the world where this is the way to go, there has to be another means of reimbursement for everyone.
Totally.
お金あげるってやめちゃって行かれちゃったら。
Besides,
You
those
see, the
infrastructures
most-
we paid for long ago.
The most important thing that we learned from this, guys, and you have to understand this, is that when the traditional power measurements are made, and everybody says, okay, if we hang a resistive load directly on an alternating current source, that is the closest thing we can come to 100% efficiency. Because I measure, let's say, 100 watts here, and I measure 100 watts at the source, and you can't do any better than that.
Right.
This proves that there's extra energy there, or I couldn't do this.
That's right.
No, but isn't that extra energy part of the phantom energy, or?
Well, call it what you want. It's still there.
True.
And what's interesting about it is,
I mean, they know about this, but they just don't know how to capture it or whatever.
Well, they don't know how to capture it because their thinking is wrong. But the other I was just going to say, when Maxwell originally was doing his fundamental work on the transmission of energy, he made the assumption that all of the energy was carried only in the electric and magnetic fields, and he did all of his equation work from that.
Right.
Years later, and it was like 30 years later, Einstein, and de Haas, who was another physicist, redid all of these experiments that Maxwell had done at an earlier time, and they found that there was additional energy that was carried by the current itself, not by the fields. And they said, oh, well, it's a fairly sizable number, but we don't want to rock the boat and change all the equations, so they just let it alone.
Gotcha.
But there it is.
That's right.